So what am I hoping to show you today? I'm hoping to take you through a couple of examples of things that will help you, pain points that I've seen folks working through in their Docker, that I think this will help you figure out why we're using it maybe a little bit more, but also help you remember what you can do to make your life a little easier. So I want to extend some of the Docker containers a little bit. I want to show you what it looks like to produce an output acceleration from a Simulink file, because that's something that you're going to need to do both for your project as well as for homework 3. And then later, not in this lecture, we're going to remap some ROS topics and show you how you can say, I don't know, how would I respond to something like that when it happens? So why are we using Docker? This was a question that came up in office hours a couple of times. Ordinarily, I would have this be like a talk to your neighbor and we can remind ourselves why. The reason why is that we've all been in versioning HE double hockey sticks at some point this semester. Something's wrong with your Python install. Something's wrong with the version of Ubuntu that you downloaded by accident. Something happened where your Simulink isn't the same as your partner Simulink, and now something doesn't work, and I don't know why I have to set localhost and you have to set remote, right? So Docker fixes some of those problems and saves you from having to download your own copy of VMware, pay $150 for a license for VMware, and then have still a virtual machine that you might have a version that's different from your partner's. So Docker is a little bit of a pain to understand why and how we use it, but it solves that problem. So what did you do for the previous example? You did Docker pull of a specific Docker image that somebody else had created. You ran it, you logged into it, and you said, run the ROS entry point, ROS core. And that gave you a terminal that had a bunch of stuff that flew past that gave you ROS, which was great. So how did this idea work, and how does Docker allow you to build on top of other versions that you have? Well, the first thing that you do is you run a bunch of commands in Docker, and then you can freeze that set of commands as an image. So for example here, I run in commands and I say, what I've just done, I never want to have to do this again. I want to freeze that version of my computer as an image, a picture that I could then load later, and then I can start from that state and move on. So if you ever want to have something that remembers what you did with the exact versions of apt that you had on that day, with the exact version of Python that you had on that day, everything frozen in time, you create an image and you freeze it then. You then can say, based on that image, now I want to do something else. So now I want to change some Docker commands here. I want to add a few new things. I want to do a git clone of something that's out there. And then once you've got that stuff frozen, you create another image. And then from image 2, you can say, I want to keep everything exactly like it was then, and I want to create some new stuff down here. So every time you're building a new layer on top of what you did before, which preserves the version of everything that you had, the file structure of everything you had, so that you can have reproducibility, which is key. So not only can you reproduce your initial state, but you can make sure that if you upgrade something, that running the same install instructions will always give you the same answers. So this is why there's a Docker infrastructure industrial complex that's out there that everybody's like, just use Docker for this, right? This is why, because they don't want to write instructions anymore or create documentation. They just want to have you start with what they had. So how do you do this? This is something that I want you to now actually maybe try. So pop open your Docker, or pop open your files. I'm going to do this over on my files. I'm going to escape from here. We're going to leave this up, but somewhere in my Docker directory here, I have a Docker file. So my Docker file, pretty simple. I start with the robot. I'm down over here in the corner. I start with the Noetic robot, and then I run ROS entry point, which was the first thing that you did before. And then I echo that into all future calls, so that in the future I'll always run ROS entry point every time I log in. And then I'm going to run ROS core. So what am I doing? I'm just doing those things one by one, so that the next time I log in, the next time I create this image, it's already running ROS core. So to build this, Docker build -t test latest, whatever I have here. Now it's going to run, it's going to build that. So it's not running it now, but it built an image that does exactly those things. And now if I docker run interactive mode test latest, it's going to start it up. ROS core is already running. I didn't have to do any of that crazy magical stuff, right? So ROS core is going, it's going in this version. If I go over and check docker ps, is that small enough for you? The blissful Gould, so docker exec -it blissful Gould bash ROS topic list. ROS is already running. Everything is good, right? So I didn't have to remember to do all those things. ROS core is already going. So this is the preview for what you can do for testing your stuff, right? You can not only have all of the boilerplate stuff run in your own custom Docker image, but you could do something even cooler. You could take the code that you're going to generate from Simulink and go ahead and have it automatically start up in a Docker image and run it. So let's see how you would do that. Let's go back to our presentation now. If you start with this version that I put you here, this runs the ROS entry point here. You run the command ROS core, but this doesn't actually, this version, if you run this verbatim, this doesn't actually put in the ROS entry point startup for every time. And so if you try to log into a new one and list the ROS topics, it'll fail for you unless you actually add that other line to the Docker file like I did. So that's this line here, echoing ROS entry point.sh to your bash RC. So this is the version that I just ran. The previous version didn't have that piece. So if you run the first one, it'll fail. This is why the slides kind of explain that. Okay, so now we're running. We can see everything. The next pieces that I would do in a Docker container is that I would, well, let's go ahead and create the Catkin workspace. Remember how every time you logged in, you had to do Catkin create workspace and Catkin make, and you would forget to do that the next time and it wouldn't find Catkin make. Well, you can automate that and put all of those in the Docker file as well. You can even copy in your bag file automatically from your local directory so that when you load your Docker container and run it, the bag file is already there. You could even have a launch file that plays that bag file again automatically. So I'm going to see if I can get to that by the end, but first I'm going to show you a couple of pieces of what does acceleration-based control look like in Simulink. So this is one of the simplest versions of how to do this. This is a dumb controller. Dumb, simple controller. This is the simple controller. Elegant, I love it. What am I doing? Well, if you had a telescope, you could see the annotation that I created in Simulink and it would tell you. So I'll read it for you after I put on my reading glasses because it's even too small on my screen. Here's the idea. When we are following a car, we try to track its speed. Whatever that car's speed is what I'm going to set my speed to be. If my speed is going too low, I'm going to speed up, et cetera, et cetera. When we're not following a car, we use the same speed we have right now. We only want to try to follow the lead vehicle speed when a lead vehicle is ahead of us, aka when we've received a relative velocity command that's a valid command. So there's a couple of pieces of logic in here. This file I'll put up on YouTube. This file I'll put up on Brightspace so that you can see it and use it. It's got a switch here that's listening to the isNew message from relative velocity. If that isNew message ever disappears for more than, I think, half a second, it outputs a value of 0. And that output of 0 then becomes, I want to maintain a 0 acceleration. So my target acceleration should be 0. And the output here, otherwise as a safe value, is the difference between the speed of the car ahead of me and me, which is already encoded as a relative velocity. So I don't have a feedback loop here. The feedback loop that measures the error between me and the car ahead is already handled by this thing. And then I just output that as a command acceleration after I do some control magic here. So this control magic is up to me. How do I know what values to choose in that box? Well, let's see. I'm going to try to create some canned data with some repeating sequences, and then I'm going to look at, well, if I speed up and slow down, speed up and slow down, speed up and slow down because a car is pulling ahead of me, I want to see whether this PID controller would actually do a pretty good job. And I'm going to do that by pretending like I'm sending that acceleration command to a car and then outputting the actual speed of that car as a relative velocity. So let's see now what that might look like. So in this case, the relative velocity is this blue here. And then this is the commanded acceleration. I speed up and I slow down, I speed up and I slow down. And so you can see that I'm speeding up and slowing down and speeding up and slowing down and speeding up and slowing down, just like the car ahead of me. So I'm trying to match that car's speed pretty well. I think it says relative velocity. This is not actually the relative velocity. This is the actual velocity in blue of my car, not the relative velocity. So if you want to see what that looks like, we can now look inside of Simulink at, let's see, Professor Project Prototype. I think I have one more minute here to sort of show you what this looks like. And it's important, I think, for you to check to see what accelerations am I actually commanding based on the speeds that I'm doing. So if we try to fit this to the screen here. So this repeating sequence, every 20 seconds goes between -2. So I'm going to be slowing down, slower than you at 2 meters per second, or faster than you 2 meters per second. And it's just going up and down, up and down, up and down. And so I'm directly giving myself this. Again, this is not the relative velocity. This is just my velocity. And it's outputting this command acceleration, which is coming back here as an input to the car. So if I run this, it's going to pop up the results after I click on the scope. You can see my velocity going back and forth between 10 meters per second, slowing down to 8. And this kind of tracks, right? The guy's going 2 meters per second slower than me, so I try to slow down. I finally get to being 2 meters per second slower in about 8 seconds. But then they're already speeding up then, so I got to try now to speed up. So this mimics some of that dynamics that you would typically see from a car. And it also confirms that I'm not sending crazy acceleration and deceleration commands here. So my output acceleration when I'm trying to slow down is about -0.5. So that's realistic. It's not going to frighten us if we see a -0.5 acceleration. If this was -50, we'd be freaking out, right? So that's cool. What if instead I want to have it be a square wave, so I can bring it up here and attach it to this square wave and then check to see when I'm having people that disappear, aka the car's not in front of me, what do I do? Well, now I can see that here I'm maintaining my current speed. So when the car disappears, I level off and I do what I should do. I just go the speed that I'm going now. When the car pulls in front of me at 2 meters per second faster than me, I try to speed up and then I level off. I try to speed up and then I level off. So again, it seems legit, right? It seems like I'm getting the behaviors that I want. But I also, in the meantime, created this other like pretend car. This pretend car gives me the ability to simulate how fast I might be going if I outputted a speed to another car. So that's where I want to pick up on Tuesday. I want to make a new ROS node that just pretends like it's receiving my command input. And then I can produce as an output its velocity. And then you could, as you put the pieces together, say, I'm not going to just look at what my output desired acceleration is. I'm going to use the bag file that tells me how a car was moving and pretend like I'm following that car. And I'm going to create something else that measures the relative velocity between me and data that I have from a real car. And I'm just going to try to follow it. And I'm going to then put up a plot and see how well did I follow that car based on these granted made up dynamics of a car. That's representative but not going to be exactly accurate. This is what Dan was talking about as well, that you don't actually get the acceleration you ask for, you get the acceleration you deserve. Okay, that's the Chester L. Carras version of control systems. But this is going to make it so that you don't immediately request 3 meters per second squared deceleration and then find that you freaked us out. Right? So I think that this is a great place to stop. Look at the slides to start easing your pain points and start creating your own Docker containers for what you can do. Send us some questions if you've got them, and we will see you all on Tuesday.